This is a load line when ID is equal to 4 milliampere and VGS is equal to minus 4 volt. If ID is 4 milliampere, this is the point, and if ID is 8 milliampere and VGS is equal to minus 1, this is the point. This is the load line. This is a load line we have to draw to find out the proper Q point. Here is the Q point from the graphical solution. IDQ is 2.6 milliampere and VGSQ is the minus 2.6 millivolt, and this is the Q point. This is the load line, and this is the transfer characteristics. Now the third bias is the voltage divider bias, where the input or the gate side supply is a sinusoidal supply, whereas the main power supply is VDD. This is a type of voltage, but here we can see different new element has been added, that is the input capacitor. This is the voltage divider circuit R1 and R2. This is the drain resistance, this is the source resistance, this is the coupling capacitor, this is also, so C1 and C2 are the coupling capacitor, this is bypass capacitor, and R1 R2 is the voltage divider circuit. This voltage divider, so this R2 will basically keep gate to source voltage as per the biasing need, and this R1 will keep the gate to drain voltage or drain to gate voltage as per the biasing need, and this C1 and C2 is for filtering the input. C1 is the filtering the input signal and C2 is for filtering the output signal. So it will filter any DC component present inside the input signal, input AC signal. If there is any DC component, it will block the DC component. Only AC component will pass through the capacitor. Similarly, in case of C2, when the output will come from this terminal, it will block any extra signal or any noise in the circuit, any DC noise in the output signal, and only the pure AC form of signal will be given to the output side. And this is the bypass capacitor. So it will use to reduce the loss in operation. So if this is a purely capacitive current, or is a purely capacitive purely sinusoidal signal, so all the current will pass through this line. If it is a DC, so DC current will pass through this RS resistance. It will be when it is passing through this RS resistance, it will be dissipated as heat. So only the pure sinusoidal signal will be processed further. Okay, so VG is here. VG is equal to R2 by R1 plus R2 into VDD, that I was talking about. So VD, as this the upper line all are VDD, so common supply. So this VDD value will be divided in between R1 and R2, and the voltage drop across R2 resistance will be appeared across gate to source terminal. This one actually. So sketching network equation for voltage divider. Achha. Okay, so this is the load line and transfer characteristics for the voltage divider bias. This is somewhat different. The transfer characteristics is same like the other biasing, but here the load line is coming from the very positive side, so it will be somewhat different here. So we can see that the VP inch of an IDS is at same point, but the load line is coming from here, so the Q point is over here. So at the junction point, means where it is crossing the y-axis, VGS will be 0 volt, ID will be VGS by RS. So some VDS value will be there, and before that VGS is equal to VG minus RD RS. Okay, so it is in positive side of the VGS, but in JFET there is no positive axis for VG, means there is no operation of positive gate to source voltage. So that's why we only talk about this portion of the graph where the Q point is situated. So here again we are seeing VGS is equal to VG, VGS where ID is equal to 0 milliampere, and ID is equal to VGS by RS where VGS is equal to 0. VGS minus VGS minus RS is 0, VGS minus VG minus VRS, and VGS equal to VG minus ID RS. Okay, so this is the very common KVL equations that we need to form to analyze the circuit that we have also deduced for the self bias circuit and other biasing. That is not new, so I am not discussing it again. Achha. Example of a problem of a voltage divider bias. First, let us see the problem. So this is the input side, this is the output side, and this is the filter capacitor 5 microfarad. This is the output filter capacitor of 10 microfarad. We have a bypass capacitor of 20 microfarad. We have a voltage divider circuit of two resistance 2.1 mega ohm and 270 kilo ohm, and drain resistance of 2.4 kilo ohm and a source resistance of 1.5 kilo ohm. And VD means the main source is plus 16 volt, where the input voltage is not defined. The only defined parameter of the JFET is IDSS of 8 milliampere and pinch off voltage of minus 4 volt. That means at minus 4 volt, 8 milliampere of current will flow through this device or through this JFET. And you have to find out different parameters: IDQ, VGSQ, VP, VD, VS, VTS, VDG. Okay. Okay, VG. So let us find first the voltage across gate to source, or the VG, gate supply. So this will be this is R1 and this is R2. So R2 by R1 plus R2 into VDD. VDD is 16 volts. So R2 R2 is 270 kilo ohm divided by 2.1 mega ohm plus 270 kilo ohm, or 0.27 mega ohm, into 16 volt. So 1.82 volt of VG will be working over here. Now VGS is, so if this is the VG, if we are means if we think about VG over here, so we have VGS here. So VGS is equal to, VGS means the voltage across gate to source. This is the gate terminal, this is the source terminal, and the voltage appear across this will be VGS. So VGS will be VG minus ID, this current, into RS. Into RS means this source resistance. So 1.82 volt minus ID into 1.5 kilo ohm. Now as the exact means the ID value is not this is the variable. So for drawing the uh, transfer characteristics, we need different value of VGS with respect to ID, or ID in respect to VGS, whatever it is. So now we have an equation that has VGS and ID variable. So we have to put different value of ID, and we have to find out in which case of VGS we will get that amount of uh, current. Okay, so first ID at 0 milliampere when no current is flowing, that is VGS 1.82 volt. Then VGS equal to 0, just opposite, VGS equal to 0. Then ID will be 8 milliampere. VGS equal to 0. When the gate to source voltage is 0, then ID is maximum. So so ID will be maximum is 8 milliampere here. Now let us draw the graph. Okay. So -4, at -4 there is no pinch of voltage, there is no uh, current conduction, so that's why it is here. And at 0 volt VGS, it is 8 milliampere current is flowing through the device, so this is the maximum IDSS or the saturation current. Now in between we have here 2 point IDQ 2.4 milliampere and VGSQ is -1.8. This point VGSQ is the at Q point -1.8 and IDQ is the Q drain current at Q point is 2.4 milliampere. This is the load line. Okay, now how to draw the load line here? VDS equal to VDT plus VSS minus ID into RS plus RD. So VDS is drain to source voltage, and VDD is the main power supply between drain to source, and VSS is the uh, voltage at source minus ID into RS plus RT minus ID into RS plus RT, that we know drain current, RS is the source resistance and drain resistance. So here VDS plus VS is equal to VDS plus VS is equal to 8.82 plus 2.6 means 11.42 volt. 11.42 volt. So this is another problem. Let us see what it gives. So VDD is 20 volt, RT is 1.8 kilo ohm, RS is 1.5 kilo ohm. Another voltage which has been given TSS. So another voltage has been connected here, that is -10 volt without any gate supply separately, and IDS is 9 milliampere. Pinch of voltage is -3 volt. So we have to do the same thing for this circuit also. So VGS plus IDRS minus 10 is equal to 0. This side of the equation, VGS minus 10 is over here. So VGS minus 10 plus ID into RS. ID into RS means 1.5 kilo ohm. So VGS equal to 10 minus ID into 1.5 kilo ohm. When ID is 0.0 milliampere, VGS is 10 volt. So when no current, VGS is 10 volt, there is no current, means when VGS is positive, so there is no current flowing uh, through the device. Now at VGS, so VGS is gradually decreasing from plus side to minus side through 0. So when VGS is 0 now, then the drain current is maximum. So that is IT 10 means 10 volt by 10, 1.5 kilo ohm, that is 6.67 milliampere. Okay, so this is the maximum current through this. Now as uh, VGS decreases, or we should say increases in negative side, the current will gradually decrease. So this is the equation. This is a transfer characteristics for the circuit given. This is the Q point. This is the load line, and this is the Q point over here, where IDQ is the 6.9 milliampere. That is here, and just below the 7 milliampere line, and VGSQ or the voltage gate to source voltage as Q point is at 0.35 volt here. So if we think about the KVL at the drain to source side, so it will be VDS equal to VDT minus VSS minus ID into RS plus RD. So VDD we know that is 20, VSS also we know that is plus minus 10. So 20 minus plus 20 plus 10 minus ID is 6.9 milliampere, this one, and the RS value is given 1.8 kilo ohm, 1 point, and RT value is given 1.5 kilo ohm, total 7.23 volt, and this is the 7.23 volt is the voltage at which at Q point, and similar at 7.23 volt the VGS value we have to find out, that is so VDD minus IDRD 7.58. So Vs is equal to VGS is minus 0.35 over here, and Vs is equal to Vt minus Vds. Vs is equal to Vd minus Vds. So Vd is the drain supply, that is the main supply, and Vds is the drain to source voltage. So 7.58 is the Vd value and Vds is 7.23 value. So we have a Vs value of minus 35 volt. So minus of VGS equal to minus of Vs. So minus 0.35. So this is another exercise. So here the question is RT and RS. You have to find out RT and RS value in if the circuit is this one. So see here we can see at 0 the maximum drain current is 6 milliampere, whereas pinch off the current is obviously 0. The pinch off voltage is minus 3, whereas the drain current is 6 milliampere. So RD will be VRD by IDQ. So IDQ and the Q point value has been given, that VGSQ is minus 1 volt and IDQ is the 2.5 milliampere. So by VRT is VRT by IDQ. So VRT is VDD minus VDQ. VRT means basically the voltage drop across RT resistance. So that means ID into RT. So VDD is equal to how much? 20 volt, and VDQ is 12 volt divided by IDQ current 0.5 milliampere. So we will get a RD value of drain resistance value of 3.2 kilo ohm, and the RS will be VGSQ means minus 1 divided by IDQ. Minus of VGSQ means minus minus plus will be there. So 1 by 2.5 milliampere. So total, so it will give us 0.4 kilo ohm of RS resistance.